Igor, for the invitation, and it's always great to come here, and especially if the weather is as nice as today. Yesterday I was worried, but today is a little bit better. And let me start by saying that I don't know much about quadruple, superconductivity, but Igor thinks that these Moiré systems might be candidates for this. So I'm going to give you an overview of some of the research that has been going on in my group regarding superconductivity Moiré systems, and then I'll tell you also about some of the latest, which again is some of the aspects are a bit unusual, and maybe indeed. But I hope mostly the homework is on you to decide whether they might be good candidates or not, or what type of superconductivity do these systems have. So let me start just because I know not everyone is an expert on Moiré systems. So we have traditionally two platforms to investigate strongly correlated and topological physics. One is traditional quantum materials with lattice scales of the order of an angstrom, and temperature or energy scales which vary depending on the material system, but they can be on the order of 100 or even 1,000 Kelvin for some of the parameters. And then this is very hard to understand, theoretically. So about 20 years ago, a new platform, ultra-cold atoms in optical lattice, was developed, because here we have a much more control over the parameters of the system. We shine lasers, create this periodic potential, and then we can tune all of the parameters in the system, and in particular the interaction strength. So that's something that has been quite fruitful. The temperature scales here are much smaller, because these lattices are, because the length scales in these lattices are much larger, of the order of a micron. Yeah? And although we have exquisite control over all the parameters of the system here, the cold atoms community is still relatively in the high temperature limit, usually in their experiments. They would like to go much lower in temperature, but it's quite hard technically. And as a result, we have many more phases of quantum matter using traditional quantum materials than what you can explore nowadays with cold atoms. And in the past few years, a new platform has emerged, Moiré quantum matter. Now the length scale is sort of intermediate, another 2 orders of magnitude from either in between these two platforms, with intermediate temperature scales also. And we have also an intermediate degree of control, not quite as much as the cold atoms, but quite a bit more than with traditional quantum materials. And the difference with cold atoms is that although we do not have as much tuning parameters, and as much, we have many tuning parameters, but not as much control as the cold atoms, we have been able to realize as a community pretty much all of the phases, or most of the phases of quantum matter that exist in materials, and also a few new ones that didn't exist earlier. So the thing that initially enabled this thing was something that now sometimes is referred to as twisttronics, which is the fact that we can stack two two-dimensional materials on top of each other with any arbitrary angle of rotation between the two crystalline lattices that we want. Okay? For my devices, I do this at a fixed angle, any angle that I want, but fixed. Nowadays, actually, you can tune continuously the angle, with some instruments, known as quantum twisting microscope and others. And the nice thing is that when you do this, and you create this Moiré pattern, and you change the number of electrons, or you vary a little bit, the symmetries that you break in the system, etc. With very few materials, you can pretty much realize, all of the phases of quantum matter that we have. Okay, and this has happened very fast. The last most spectacular one, the realization of fractional chain insulators in two different Moiré platforms, twisted systems. So this is something that is, is very rich, and that a lot of people are investigating. So what do I want to tell you about today? I want to start by telling you about the magic angle multilayer graphene family of Moiré superconductors. That was the first that was discovered, and it has many members now, and I want to tell you about the characteristics of it. And then I will tell you about our latest study doing simultaneous transport and tunneling spectroscopy of a Moiré superconductor, in particular magic angle twisted trilayer graphene. We're combining both techniques. We have now a distinct observation of the superconducting gap that I would argue it was not really seen before, and where we have quite a few pieces of evidence for nodal superconductivity in this system. This is also a very strong superconductor, as I will mention. So let me get started with this. So what is magic angle and twisted bilayer graphene? So we have two graphene sheets on top of each other, rotated by a certain angle, the magic angle, 1.1 degrees. But let's start first from just two graphene sheets rotated on top of each other. The Dirac cones of the electron to the electron energy momentum dispersion in layer 1 and layer 2 are like this. And these Dirac cones are separated in momentum space because you have a rotation between the crystalline lattices in real space. The separation in momentum space is proportional to the twist angle and for small angles. Now this would be the situation that would be realized if electrons in one graphene sheet did not know about the other graphene sheet, and therefore you have this sort of crossing of electronic structures. However, because we have, when we put one graphene sheet on top of the other, these are just separated by 3 angstroms. Electrons can tunnel between the 2 graphene sheets, and that leads to energy repulsion. Okay, at the energy of that crossing point, you have band repulsion. And this is the same thing as bonding and antibonding states for a hydrogen molecule, but this is bonding and antibonding bands for a giant twisted layer graphene molecule. So that leads to some band repulsion due to that interlayer tunneling. And this is the situation when the interlayer tunneling is much less than the energy of that crossing point. But if we now push, we decrease the twist angle, these 2 cones get closer and closer together, and that crossing point gets pushed down to lower and lower and lower energy, okay? And the band repulsion therefore pushes the bands towards lower and lower energy until you reach, when this interlayer tunneling is of the same order as the energy of that crossing point, you reach what is known as a flat band condition. And this is realized at 1.1 degrees for graphene on top of graphene at ambient pressure. Yeah? So that magic angle term was coined by Bistrisser and McDonald in 2011. At about the same time, there were also other single particle theory calculations that established that there was indeed the presence of a flat band. And the group of Eva and Ray had done some interesting scanning tandem microscopy experiments where they saw this, Van Hoff singularity, a peak in the density of states in those regions that extrapolated to 0 at 1.1 degrees. So there was already about, about this time, now 15 years ago, compelling evidence, theoretical and experimental, that the single particle effects of flat band would happen in these systems. And then, if you have, this was a cartoon, right? This is an actual calculation of the energy momentum dispersion for magic angle twisted layer graphene. These are the flat bands. As you can see, they're not mathematically flat. There is a little bit of dispersion, but it's orders of magnitude, smaller Fermi velocity than for the original graphene dispersion. And then if you look at, if you put electrons in these flat bands, this is a momentum space. Where do they like to sit in real space? To do that, you have to do a Fourier transform from momentum space to real space, and flat band in real space is a highly peaked object. So you have these regions, electrons in these flat bands, they like to see in regions of AA stacking, okay? And they do not like to see it as much in regions of AB, BA stacking. So schematically, you can look either here or here. This is a slightly more realistic schematic. Magic angle twisted layer graphene looks like this. There are these regions of AA stacking. They're spaced about 13 nanometers. And they're separated by regions of AB and BA stacking. Here, in these regions, the electrons like to be. This is sort of to be an analog of a triangular Fermi-Hubbard lattice for cold atoms. Yeah? Except that I put many things in quotes here. Triangular. This is not really triangular. It's honeycomb because AB and BA is not the same. And Fermi-Hubbard in quotes because this lattice has the electronic structure of magic angle twisted layer graphene has certain topological properties that prevent a direct mapping to a vanilla Hubbard, lattice of the usual type in cold atoms. But that's sort of the spirit. Okay, put electrons there and make them interact and see what happens. So what happens is that if you measure, the conductance of this system as a function of density, there are regions of density, okay, which correspond to 1 or 2 or 3 electrons per Moiré unit cell. In these original experiments, there were the 2 holes and the 2 electrons per Moiré unit cell, which are insulator, even though they should be good metals. So these are correlated insulators. And then these things happen only for devices with a twist angle with a narrow range around 1.1, basically 1.1 plus minus 0.1 degrees, more or less. And then if you dope a little bit away from these regions, you get electrically tunable superconductivity. Okay, so that is what we discovered in my group now 7 years ago. Yeah? Now, the superconductivity in magic graphene is robust superconductivity. And by that I mean that you have zero resistance. The devices. I mean, by now discussing on my hundreds of groups, there are hundreds, dozens of groups. You have flat current voltage characteristics with sharp switching. And you also have, we don't have Meissner effect in 2 dimensions, right? These are 2-dimensional superconductors. You don't have proper Meissner effect. The field always penetrates. But the next best thing that you can have to show that something is a superconductor is just a surface coherence. And you can realize here, gate-tunable Josephson junctions, and you can see Josephson patterns. You can also, people have measured also the AC Josephson effect, Shapiro steps, everything. So it's a well-characterized by now superconductor. And I'm showing data here from my group, but, robust superconductivity has been reproduced by many, many groups, all over the world in these systems. Now, there are other Moiré systems where the superconductivity is more fragile, or people have doubts whether it is or it is not superconductivity, okay? And only very recently, 2 papers have argued that there is also robust superconductivity in the twisted transition method like chalcogenides. It's a very nice type of superconductivity with some similarity, but also some difference to the graphene-based systems. I'm not going to talk about it, but I wanted to mention it, that the field keeps finding new superconductors in these strongly correlated Moiré lattices. So now, is magic angle graphene the only robust Moiré superconductor? Okay, and initially people didn't know, but it turns out there is not a unique system. There is a family of superconductors, okay? And in particular, the second member of the family to be discovered was this mirror-symmetric magic angle twisted trilayer graphene, okay? So where you have 3 sheets of graphene twisted, the second sheet is twisted by an angle theta on top of the first one, and the third sheet is twisted by an angle minus theta with respect to the second, so back parallel to the first one, okay? That's called, mirror-symmetric or the alternating twist geometry. So, 2 groups, my group and the group of Philip Kim, we reported, back to back in the same week, the discovery of tunable, strongly coupled superconductivity in magic angle twisted trilayer graphene. And then it's not only 3, but we call this Moiré magic 4.0 and 5.0. 2 groups, Stefan Machperz at Caltech, my group, and also related work by the Tutu group at UT Austin showed that also 4 and 5 layers in this alternating twist geometry give you robust and strongly coupled superconductivity. So by now, we believe that this is just, 4 members. That already makes a decent sized family by today's standards, But this is an infinite member family because the conditions for these flat bands have been calculated all the way to infinity. Okay? Let me tell you a little bit about this alternating twist family, and in particular, we'll start with mirror symmetric magic angle twisted trilayer graphene. So as I said, this is you have a sheet, and then you twist by minus theta, and then you twist back by theta. This is a geometry that was predicted by the group of Ashwin Viswanath, by Eslam Khalaf. And it's called also twisted A type of stacking. The first and last layers and third layers are exactly on top of each other, not only at the same angle, but aligned also. Okay? If you do, and there's a lot of work on similar geometries and related interlayer systems, etc. So the nice thing about this twisted trilayer graphene in this alternating twist geometry is that you can think of it as magic angle twisted bilayer plus graphene. Okay, so you have this tunneling between adjacent layers. So what you do is you can change the basis of your Hamiltonian and do a rotation such that the Hamiltonian becomes block diagonal, and you have one block is magic angle twisted bilayer graphene with a square root, with a normalized tunneling, square root of 2 times t, and then just a single diagonal block, which is graphene, single layer graphene. Okay? Because the magic angle condition depends on this interlayer tunneling. In this case, the magic angle for the trilayer is the magic angle for the bilayer times square root of 2, because of the square root of 2 times t. Okay? So it's actually about 1.56 degrees. And this means that the Moiré wavelength, instead of being 13 nanometers, is a bit shorter because the angle is a bit larger, so it's about 9 nanometers. And this is the electronic structure in the electronically symmetric configuration without a displacement field applied out of plane. And what you can see is that you have this set of flat bands, and then you have an additional graphene Dirac cone, the usual massless Dirac cone of electrosync graphene. Yeah? Now, in our devices, we have magic angle twisted bilayer graphene in a field effect transistor geometry, which means we make a parallel plate capacitor between the magic angle trilayer graphene and a metallic plate so that we can change the density of electrons. Well, we have 2 gates, a top and a boson gate that allows us to independently change the density of electrons in the system, and also the displacement, the vertical displacement field, which breaks the mirror symmetry. When we break that mirror symmetry, now we can hybridize the bilayer graphene and the monolayer graphene sectors. Okay? So the electronic structure is tunable. At zero displacement field, the states here and the states in the flat band, they are orthogonal. Okay? Now we can hybridize them. And we have a tunable degree of hybridization between these systems. Okay? So because of this tunability, the tri-layer, magic ion tri-layer is a bit more special and tunable and interesting than the bilayer case. Now, if you measure these devices, you find again, zero resistance, flat voltage current characteristics. You can have Fraunhofer patterns. This is electrically tunable superconductivity as a function of doping, which here is exemplified by the filling factor, which is the number of electrons per Moiré unit cell. And this is, the map of superconductivity here is in light blue. This is versus displacement field and filling factor, and you can see that there are many regions, and we can study in each region what happens with TC, with the coherence length, with all of that thing has been mapped, and you can look at in these papers. Okay, let me just tell you a couple of things. This is sort of old news in quotes, so I'm going a bit fast. I will slow down when I get to the more interesting recent news. But one of the things which is quite nice about this system, quite interesting about these systems, is that if you plot in log scale, critical temperature versus Fermi temperature, this is one way of characterizing the strength, in terms of physics, the strength of a superconductor. Okay? This is called a Uemura plot. I should have, usually in the slide I have reference here, but somehow it's missing. But this was studied by Uemura at Columbia, already 30 years ago in the context of the cuprates. He noticed that while typically, weakly coupled BCA superconductors are typically near this corner. They have extremely high Fermi temperatures. These are, very good metals with modest critical temperatures. All of the unconventional superconductors, the cuprates and the pnictides and the heavy fermions and the organics, they all lie in sort of this purple region where you have relatively high critical temperature compared to the Fermi temperature. All these systems have much smaller Fermi temperatures, and their critical temperatures are higher than the weakly coupled BCA superconductors. So magic angle twisted bilayer and especially tri-layer graphene, their data points here. Okay, they have extremely low Fermi temperatures of the order of 10, 20 Kelvin, but they have TC's critical temperatures of 1, 2, 3 Kelvin. These are the most strongly coupled superconductors that we know. Yeah? If the cuprates had the same coupling strength, they would be well above room temperature superconductors. Yeah? And this is something that I'm showing here my data. The group of Ginny Lau claims with a different technique for extracting the Fermi temperature that those data points are actually up here, a factor of 10 higher. Okay, so regardless of whose measurement and whose technique and determination characterization of parameters you trust, these are extremely strongly coupled superconductors by any standard. And we do not know exactly why. How come that a system that has an electron every 10 nanometers or so, an extremely diluted system, can pair electrons so strongly that they superconduct at the same TC as aluminum that has 4 orders of magnitude higher Fermi temperature? Okay, so that's something that the community is trying to understand. There are many ideas, related also, for example, to the role of quantum geometry in these systems, okay, these flat bands. That's something that is very popular nowadays, and that many groups are discussing. Of course, all kinds of mechanisms which are non-usual standard BCS mechanisms that also would justify a higher critical temperature, etc. Now, magic angle twisted tri-layer graphene is also unlikely to be a spin singlet superconductor. If you apply an in-plane magnetic field, you see that it violates the Pauli limit by a very large factor, okay, by a factor of 3, in a system with very little spin-orbit coupling, so that's very unusual. And in some of our devices, we even see reentrant superconductivity at very high magnetic field. Once you've killed it, then it reappears. Okay. Now, this is something that has been seen in very few devices, so it's not, we don't know yet exactly under which conditions or if it, but it's also the type of measurements are done because they need an in-plane magnetic field. There are a few labs that have that for standard Anderson features, so there's much less, but this is very well established, Now, it's not only 3, or 2 and 3. In this paper, Eslam and his collaborators, they told us that there is this magic angle hierarchy, okay, for where if you look at the number of layers, and then here alpha is a parameter that you can think of as 1 over the magic angle, 1 over the twist angle. Okay? So you can see that for 2 layers, there's not only 1 magic angle. Okay, this is the 1.1 degrees magic angle, but there are actually additional magic angles. Okay, this is called the second, the third, the fourth magic angle. Same thing for 3 layers. Starting from 4, actually the system splits into hierarchies of magic angles. You have the first magic angle, the second magic angle, the third magic angle, and you also have the second first magic angle, the third first magic angle, and the thing splits, into multiples of all of these. This is all theoretical. The only ones that have been discovered so far experimentally realized are the first ones, okay? We don't know if the others exist, but it's interesting that all of these others, they're not just identical copies. They actually have different topological electronic structures, okay? So there are many different properties in principle in this family of flat band materials that could lead to different structures. All of these, they can be, they have this theme, at least certainly the first ones, they have this theme of the Hamiltonian can be, rotated into a basis where you always have a magic angle twisted Vallejo graphene-like sector block with a renormalized tunnel coupling. Then you have as many larger angle twisted Vallejo graphene blocks as even numbers you have. And if you have an odd number of layers, you have always an additional monolayer graphene sector. Okay? So these are the electronic structures for 2 layers, 3 layers, 4 layers, 5 layers, and the magic angles. Yeah, as you can see, for 2 layers, flat band, 3 layers, flat band plus Dirac, 4 layers, flat band plus large angle twisted Vallejo graphene. This is not massless graphene, but large angle twisted Vallejo. 5 layers, you have flat bands, large angle twisted Vallejo plus monolayer Dirac cone, etc. And all of these, you can hybridize the different blocks by applying a displacement field, etc. So these are very rich and tunable systems where you have many different components that can enter, and they can, some of these things can be proximatized by the flat bands or not proximatized, etc. So they're very rich and tunable systems. So if you make devices with 2, 3, 4, 5 layers at these different magic angles and so on, you can, this is for, this is our highest, TC at optimal doubling device for the bilayer. This is for the trilayer. This is for tetralayer. This is for pentalayer. Okay, so we have a family of robust superconductors. Okay, and they have all been measured by several people. Maximum TC increases a little bit, but not too much. Okay, not as much as initially we thought. Oh, maybe this is a way of getting to room temperature superconductivity. No, it saturates the magic angle conditions. The flat bands, the Moiré patterns, they all saturate. There's a geometric progression that saturates, the dimensions of the system. So it was unrealistic to expect actually much higher. For those of you that pay strong attention to the archive, it turns out that when we posted our first in the archive our first version, the 5 layers, which was at 1.95 degrees, because that's what Aswin had told us the magic angle was for 5 layers. Happened to be a very anticlimactic device, it was, higher, 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 and then much lower, So that's what life is. What can we do? We posted, and then Aswin calls me one day and tells me, you know what? We didn't take into account the lattice relaxation in the calculation of the magic angles. It turns out the magic angle for 5 layers is a little bit lower. It's not 1.95 degrees. It's 1.80 something degrees. Do you mind, please? Checking, each of these devices with multiple angles and so on takes a very highly trained student a month or 2 to make, But nonetheless, my student Jane, she's very motivated, so we fabricated a new device at 1.84 degrees and superconducted at higher, TC. This don't take it too much, different devices and so on. It could be that, but it was an input of, a theoretical input which guided us in that direction, and it turned out to be all right, So who knows? Maybe indeed the magic angle is this one, not this one, for the optimum condition for the flat bands. Anyway, we don't have yet a good theoretical model of exactly how to calculate TC from the magic angle flat band condition. But I was happy, that this happened, and Aswin was very happy. He thought it confirmed his theory. So, Okay, so this is, what, this magic angle family of Moiré superconductors does and looks like. Let me tell you about our more recent studies. So superconductivity in this magic angle family, it appears under certain conditions, okay, which they don't always need to be realized, but it seems like it's strongest, the superconductivity, under these conditions. So first of all, the schematic for this alternating twist geometry, okay, the guiding principle for them is that this alternating twist geometry respects C2T symmetry in the system. And a number of theoretical proposals think that that's an important ingredient, to have C2T symmetry in the system to realize the superconductivity. The other thing that happens, which is interesting, is that there is a cascade of phase transitions, this flavor symmetry breaking. Electrons in graphene have spin and valley degrees of freedom, okay? And when you measure the inverse compressibility with the scanning singleton transistor, or this can be done also in STM, you see these bumps here, that occur, which they signify, they denote phase transitions which occur, and these phase transitions at 1, 2, 3 electrons per more unit cell, they're telling you that the system is decided, rather than the electrons having all 4 flavors, possibly, spin up, spin down, valley K prime, they decide to coalesce into 1 flavor, or into 2 flavors, or into 3 flavors, and empty the other flavors. Okay? That's something that has been measured by many people, many groups, including my own, with Shaharilani. And in transport, especially in these tri-layer systems where everything is more tunable, we know very well under which conditions superconductivity appears. In this system, superconductivity is strongest and almost always appears when electrons are in the 2-flavor regime, which means they have either chosen spin up, spin down, or valley K prime, or another superposition, but 2 out of the 4 flavors. Okay? So that means that superconductivity appears in the region between -2 and -3, between 2 and 3 holes per more unit cell, or 2 and 3 electrons per more unit cell. Okay? If you have them sometimes in these regions of between 1 and 2 electrons per more unit cell, what happens actually is that there is a reset to hold-up system within the electron system, so the effective flavor is actually 2 minus something rather than 1 plus something. Okay? And this has been all mapped out in these papers, very well. The other thing that happens is that it's likely non-spin singlet, as I mentioned. STM spectra have indicated that there are these V-shaped tunneling spectra in the superconducting regime. This was attributed in these papers that this is indication of nodal superconductivity. I will show you that these are actually not the spectra for the superconducting state. There are spectra in the superconducting state, but they don't correspond to the superconducting tunneling spectra. You will see what I mean in a moment. These systems break rotational symmetry, so the critical magnetic fields exhibit, two-fold symmetries, that are ellipses. Okay, so the systems have pneumaticity in them. Very recent papers with my collaborators at Harvard for the tri-layer case and at MIT for the bilayer case have shown, in the case in particular of the tri-layer, a linear temperature dependent of the superfluid stiffness. That also is a strong indication of nodal superconductivity. So there is a lot of indications that the superconductivity is very unusual, in addition to the strong coupling, and so on that I mentioned earlier. So we have a very complex phase diagram for magic angle twisted bilayer graphene. For tri-layer is similar, okay, where you have superconductivity and correlated insulators and a pseudo-gap regime and all kinds of, topological phases, various types, okay, chain insulators, symmetric broken chain insulators, correlated chain insulators, all kinds of things. And the question is, what else, what more information can we give to the theorists to better understand this system, okay? So many of these phases have been studied by one technique or by another, but not by 2 techniques simultaneously, okay? Because different techniques are sensitive to different phases, etc. One thing that has attracted a lot of attention is the superconductivity. It's very likely unconventional, but many of the key characterizations of superconductivity have been done either only in transport or only in tunneling spectroscopy. So we wanted to do simultaneous transport and tunneling spectroscopy in the same device so that we can compare these things. Okay? So this is what it took to do this. So we made this magic angle twisted tri-layer graphene devices, dual gated, bottom top on gate, not dual gated, dual gated, but in this geometry. We actually decided to couple two magic angle twisted trilayer graphene devices. Okay? So the structure is, we have a bottom magic angle twisted trilayer, a top magic angle twisted trilayer. They're separated everywhere by thick HBN, except in a region, in a hole there, where we have only 3 layers of HBN. 3 layers of HBN. HBN is a dielectric, an insulator. 3 layers is about a nanometer, so we can tunnel between the two magic angle graphene sheets locally in this region. Okay? It's about a micron in diameter. And we have graphite top and bottom gates so that we can tune the density of each tri-layer graphene independently. Okay? So this is 12 layers with 6 angles and so on and so forth. Now, let me tell you, so we have independent doping tunability, independent whole bar device, so we have whole bar contacts to each of these twisted trilayer graphene. That means that we can do electronic transport through each device separately, and then we can also measure interlayer transport, which is tunneling. Okay, this tunnel barrier. Now, this is the characterization of the electronic transport through each independent device separately. We have resistance of the top magic angle trilayer, okay, versus top gate. This, bright means, peaks, dark means superconductivity, so we have superconductivity between -2 and -3, between 2 and 3 as usual. Here is the resistance for the bottom magic angle trilayer. We have also superconductivity and superconductivity. We have less gate voltage range here, so the reason why these features are vertical and these horizontals is because, this is the top layer, so it's sensitive to the top gate. This is the bottom layer, so it's different to the bottom gate, okay? Now, for the purpose of this talk, the reason why we wanted to have both layers, both stacks to be magic angle tri-layer, but for the purpose of this talk, I'm going to use one of them just as a normal metallic tunneling electrode, okay? So I'm going to tune my backgate voltage to this region where there's no superconductivity and this thing is a relatively boring metal. And I'm going to use the bottom magic angle tri-layer to tunnel and investigate the top magic angle tri-layer. Okay? So I'm going to choose this back gate, and then I'm going to change the top gate. Yeah? So if I use this bottom magic angle tri-layer as a tunnel probe for the top magic angle tri-layer, this is what I get. Okay? This is gate voltage. This is interlayer bias. You should think of this as the voltage of my STM tip, except there is not an STM tip, it's a planar tunneling device. Okay? And this is very similar, okay? This in particular are the cascades of phase transitions, and there are gaps here, and there's a structure. This thing and this thing are the flat bands when they are not occupied. These are the flat bands when the chemical potential is in the flat bands. They broaden due to interactions, and things happen, okay? This is very similar to the way STM data look like for magic angle twisted trilayer graphene. Okay, you have the flat bands here and here. They come, they broaden, and then you have the cascade of phase transitions. They're like that. Okay. So yeah, and again we're tunneling through the 3 layers HBN region with about a tunneling conductance of the order of a mega ohm. So we're in the tunneling region. Now, this is what the tunneling data look like. We can do simultaneously transport through that exact same magic angle trilayer graphene sheet that we are tunneling to. Okay. Okay. So this is a cascade. This is gap regions. If we do zooming into these regions at much smaller energies, okay, you see here these 2 regions where we have very little density of states. If we actually measure the resistance through this top graphene sheet as a function of the voltage, this is what the resistance does. So you see, we measure 0 resistance here in transport, and we measure a depleted tunneling density of states in the tunneling. Okay? And we can do this thing everywhere. We can take the tunneling traces everywhere as a function of top gate. I'll go into the more details now. So these are the first simultaneous transport and tunneling spectroscopic measurements of a Moiré superconductor, where if we see now a feature in tunneling, we can unambiguously tell you if the system is in the superconducting regime or not, for example. Okay? And we can study the tunneling and the resistivity as a function of various parameters, temperature, magnetic field, and do the comparison to make sure that when something we think is superconductivity, it really relates to superconductivity. So this is, this is very much zoom in, this is very much zoom out. Let me give you an intermediate energy scale, plus minus 10 millivolts scale in tunneling. It turns out we have two gaps in the superconducting regime of the system. Okay? There is a very small gap here, the dark, ellipse, and then there are these higher energy gaps. Let me show you more detail about it. Okay? If you take here, okay, the superconducting regime, VIDV versus interlayer voltage, we have this structure, and then there is a narrow peak within it. Okay, narrow peak within it. This is the low energy gap, we call it. It has even some mini coherence peaks. And then we have here, we call this the high energy gap structure. So, these are the energy scales of order 0.1 millivolt for the low energy gap. The high energy gap is about 10 times another magnitude larger. Yeah? Let's characterize this thing. So, we can do transport through the same device at the same filling factor under the same conditions. Here is resistivity versus temperature. We can see that the TVKT for this filling factor is about 1 Kelvin. So let's see how does the spectroscopy vary, the spectroscopic gaps vary with temperature around this, okay? So if we look at the spectroscopy, and these are traces at 0.1 Kelvin all the way to 1.6 Kelvin, we can see that the low energy gap fills very rapidly, okay? It gets completely filled by the time we get to about 1.2 Kelvin, 1.6 Kelvin, okay? That is in contrast with the high energy gap, which only very slowly evolves, in the next 10 Kelvin, so to speak, okay? So, in fact, one can look at how fast does the gap fill with temperature, okay? And you can see that there's a very rapid evolution first, and then a saturation and a very slow evolution. And that happens around TVKT, okay? Around the critical temperature of the superconductor. So this low energy gap is substantially suppressed at low T, with the coherence peaks fading away around TC. Okay? The high energy gap persists to a much higher temperature of order 8 Kelvin. Okay? The low energy gap follows the temperature-dependent behavior of the superconductivity transition as measured in transport, while the high energy gap behaves more like a pseudo gap. Okay, like a gap. And pseudo gap. Let me leave it down very broad, not necessarily the pseudo gap of the couplets. We call it high energy gap in our paper, in fact. Now, let's look at what happens with magnetic field dependence. Okay? So, we can measure the resistivity versus perpendicular magnetic field, and there is a critical field of the order of 30, 40 millitesla, something like that. If we look at the tunneling spectroscopy, the low energy gap disappears very quickly on the scale of the same scale as the critical field for transport disappears. Coherence peak also disappear, whereas the high energy gap actually doesn't change much with magnetic field, even all the way to a Tesla, when we know superconductivity is way long gone, okay? At least in terms of transport. Yeah? This is a very unusual behavior for a superconducting. Yeah. Okay? So the high energy gap does not have an obvious B perpendicular dependence, even at fields as large as 1 Tesla. That means again that the low energy gap follows the magnetic field dependent behavior of the superconductivity as in its transport, while the high energy gap is not very perturbed by magnetic field. Yeah? Now, so properties of the higher energy gap. Okay? It has a relatively weak temperature dependence, very weak or no magnetic field dependence, perpendicular magnetic field dependence. This is very similar to the tunneling spectroscopy gaps observed in previous STM experiments. These are the data from the Jesdani group. These are the data from the Stefan Natch-Perch group. They had this 1 millivolt order energy gap, V-shape, in a superconducting regime. So they thought this was the actual superconducting gap, which had a weak temperature dependence and almost no magnetic field dependence, so exactly the same things that we see in our tunnel spectroscopy, except that, this type of behavior does not agree with what the actual superconductivity as measured in transport is doing, okay? So these type of behaviors, which by the way are reminiscent of some of the behaviors of the pseudo gap in, for example, cuprate and other correlated materials, okay? Although not all things are similar, I'll tell you the differences in a moment, okay? But basically this higher energy gap is something that is occurring in the superconducting region, but is not, directly the superconducting gap, or at least not the phase coherent superconducting gap, associated with that transition as measured in transport. Okay, so this gap, this very, the inner gap, which I'm now zooming in, is actually the associated with that superconducting transition in transport. Okay, this is a detailed temperature dependence. You can see how it looks like. Okay? Now, the thing is, if we want to characterize this gap, it's in the presence of this background high energy gap. Okay, so how do we disentangle the two spectra and focus only on the low energy gap? So we can look at, again, resistance versus TVKT, versus temperature. Look at what's the critical temperature. And what we can do is we can normalize the curve, all of these curves by the curve which is at temperature slightly above critical temperature. That's something that we copied, from the cuprates, where they also have two gaps and they want to normalize and extract information about one without the other. So, in this data, by Eric Hudson, this was a way of normalizing and finding the intrinsic, low energy gap. Okay, so we do basically the same thing, and this is what you get. This is a normalized differential conductance versus bias voltage. Yeah, we try to fit the data with two curves. One is an edge wave, okay, hard gap. The other one is with a nodal superconducting gap, and we account for disorder, okay. And this is the way our best fit looks like for nodal superconductivity. This is our best fit, and we've explored all parameter space, for months for edge wave. It seems that it fits much better with an overall parameter, okay, even including disorder and broadening, etc. Now, you can do the temperature dependence of all of this, okay, normalize, etc., and do all the fits, you want. And then you can look at what is the differential tunneling conductance at zero bias and how this fills, how this rises. And then you can look also at what is the gap extracted, the mean gap extracted from fitting of all of these curves as function of temperature. You can see that the low energy gap stays roughly constant at low temperature, and then once you start getting closer to TC, then it starts closing. But the DIDV, this gap starts filling right away linearly with temperature, already from very low temperature. Okay, that is a behavior which is more consistent with nodal superconducting behavior than with a hard gap behavior that would require an exponential rise as a function of temperature as you get closer to TC. Now, what happens when you apply to the superconducting gap, when you apply magnetic fields in either the perpendicular or the parallel magnetic field direction? So I'll accelerate a little bit because I think I'm running out of time. But basically, you expect to have a square root B perpendicular dependence of your, behavior, your tunneling conductance when you have a nodal superconductor. This is known as the Bolovic effect. Okay, if you take in our dome, of resistivity versus doping and magnetic field, this is the way tunneling looks like at this filling factor. This is the way resistance looks like. This is the way the tunneling conductance looks like. Okay, so this behavior seems to be consistent with the Bolovic effect. If we do an in-plane magnetic field dependence, you again are expected to have a rise in the tunneling conductance. Okay, linear. Okay, for as you destroy your superconducting pockets there at the nodes. This is the way transport looks like. This is the way the tunneling conductance looks like. We have a little bit of a rounding at the very lowest temperature, but way before you get out of the critical magnetic field, you are already rising semi-linearly. Okay? So we have these four pieces of evidence that, consistent with the nodal superconducting gap. Oops, sorry. And this is reproducible I've shown data from, one doping regime, electron or hole. It's everything reproduces on the other one and reproduces on different devices. Okay. So with this, I'll just skip this. This is just the dependence of the superconducting gap on the critical temperature, as the superconducting gas proportional to Tc. It also happens to be proportional to the superfluid stiffness, as we have seen in the other experimental studies. And let me just say that the high energy gap, if we do the dope independence, okay, with the electric field, okay, so it's electrically tunable, we see that the high energy gap it also roughly, not precisely, but roughly follows the superconducting dome, okay? Which means that the high energy gap is something that occurs in the superconducting regime. So it's probably related to superconductivity, but it's not the superconducting gap in the sense of the behavior, is not the same as the superconducting phase coherent transition, So we still need to know what that is about. And this is a summary, but then we go to the acknowledgements. All this work was largely done by my grad student, Joan Sa, before he moved to Harvard and Berkeley, by Jane Park, she just moved to Princeton, and by Shu Wen, who's still in the lab, and Daddy. And thank you all for your attention.
Thank you very much. A couple of quick questions.